In the previous lesson, frequency response told us how a circuit treats each sinusoidal frequency. Now we turn that language into two physical circuits. A low-pass filter keeps the low-frequency part and reduces the high-frequency part. A high-pass filter does the opposite. Same resistor and capacitor idea, same corner frequency, but a different output node. Think of a filter as a frequency selector. The pass band is the region we want to keep. The stop band is the region we want to suppress. The cutoff frequency is not a hard wall. For a first-order passive filter, it is the -3 decibel point, where the amplitude is 1 over square root of 2. Start with the RC low pass. Put the resistor in series, put the capacitor to ground, and measure the output across the capacitor. At low frequency, the capacitor is almost open, so very little current flows and the output is close to the input. At high frequency, the capacitor becomes an easy path to ground, so the output node is pulled down. The result is H low pass of j omega equals 1 over 1 plus j omega tau. Now move the output to the resistor side after a series capacitor. This is the RC high pass. At low frequency, the capacitor blocks change, so the output across the resistor is small. At high frequency, the capacitor behaves almost like a short, so the input reaches the resistor and the output approaches the input. Its transfer function is j omega tau over 1 plus j omega tau. Both circuits share the same time constant, tau equals RC. The corner angular frequency is omega c equals 1 over tau, and the ordinary cutoff frequency is fc equals 1 over 2 pi RC. At that corner, both magnitudes are 1 over square root of 2, which is -3.01 decibels. The low-pass phase is -45 degrees, while the high-pass phase is +45 degrees. On the Bode magnitude plot, the two curves are complementary. The low-pass starts near 0 decibels and then rolls off at about -20 decibels per decade after the corner. The high pass starts very small, rises at about +20 decibels per decade before the corner, and then flattens near 0 decibels. The phase plots tell the same story in another language. The low pass starts near 0 degrees and approaches -90 degrees as frequency increases. The high pass starts near +90 degrees and approaches 0 degrees as frequency increases. At the corner, the phase values are symmetric, -45 and +45 degrees. A first-order RC filter is easy to design. Choose the cutoff frequency, choose either R or C, and solve for the other one. For example, if Fc is 1 kHz and C is 100 nanofarads, then R equals 1 over 2 pi FCC. That gives about 1.59 kiloohms. In practice, you choose the nearest standard resistor value. 4 traps to avoid. First, the output node decides whether the same RC pair is low pass or high pass. Second, omega c equals 1 over RC, but Fc equals 1 over 2 pi RC. Third, passive first-order filters are gradual. The cutoff is not an ideal brick wall. Fourth, real source and load resistance can shift the cutoff unless the filter is buffered. Summary: low-pass and high-pass filters are frequency selectors built from the same frequency response idea. For first-order RC filters, tau equals RC, the cutoff is 1 over 2 pi RC, and the cutoff gain is -3 decibels. Changing the output node changes which side of the spectrum is kept. Next, we add a second energy storage element and meet bandpass behavior, resonance, and Q.